Okay, I think we should start, and it is a great pleasure to have with us Zaharias Roupas, who's going to be giving today's seminar entitled Statistical Mechanics of Gravity and Gravitational-Wave Emission by Binary Black Hole Mergers Inside Stellar Clusters. And Zahos actually obtained his undergraduate degree in physics from the University of Athens and his PhD from the National Technical University of Athens from in 2013. The title of his PhD was in thermo-gravitational instabilities of spherical I cannot really translate that, sorry about that. Fluids, spherical fluids in the presence of cosmological constant. And he actually spent some years in the British University of Egypt, and we are very happy that starting 2022, he decided to move back to Greece, or to Crete in particular, where he's going to be spending some time, and he's actually teaching math in our freshman physics students. So without further ado, I'll give the floor to Zahos to talk to us about his results. Thank you.
Okay, thank you very much for introducing me, for inviting me here. I'm very, very, very happy to be in the Department of Physics. Now, I will talk about my research, actually. So this talk will be around my personal research program, but also I will give some basic stuff about the clusters, stellar clusters, and the binary black hole mergers. So what I have been working on is thermodynamics of the gravitational interaction and the statistical mechanics with applications in astrophysics. And when I say astrophysics, I mean stellar clusters, dynamics of stellar clusters, and compact objects, actually. So let me start with a phenomenon that I have given to the community that I call, and it's called relativistic gravothermal instability. Now, consider the Newtonian case. So, I mean Newtonian gravity. So, assume that we are in the weak field limit, and assume that you have a sphere that contains gas molecules that interact with each other only through gravity. So in the system, you have only motion and gravity. And let us say random motion. So random motion is thermal energy, is heat. Now, the thing is that random motion, heat, thermal energy, generates a pressure, okay, that points outwards. This means that it gives the gas the tendency to expand, okay? On the other hand, gravity have the opposite effect. So gravity makes gas tending to collapse, okay? So you have motion, random motion, and you have gravity. I said before that I consider the case of the molecules interacting only with gravity. This means that I'm referring to the case of ideal gas. Ideal in the sense that there are no molecular forces, no nuclear forces, and so on. Okay, so it is an ideal gas, but it is a self-gravitating ideal gas. Now, for such a system, in the weak field limit, it has been found back in 1962, 60 years ago, that if you cool the system very much, equivalently, if you expand the system, so if you inflate the sphere of gas, then an instability will set in. In fact, there will set in two instabilities. One instability is called Anton of Instability. So Anton was the guy that introduced this instability in 1962, as I said. And in this spiral here, it is point B. Now, what is the essence of this instability? You see in the x-axis, x-axis here, that we'll have the energy. Okay, consider R the radius of the sphere, and this M, calligraphic M, is the mass. Consider it constant. What's the radius and the mass? So here we'll have the energy, and in the vertical y-axis we'll have beta. Beta is inverse temperature. So this is a caloric term. This is how it's called. You have temperature versus the energy. At very low energies, or equivalently low temperatures, you see that there is a threshold denoted by this line here, beyond which you cannot have any equilibrium. So what is this curve here representing? It represents a series of equilibria. Every point here is a thermodynamic equilibrium. It is also dynamic equilibrium. Again, each point here represents an equilibrium. So the area on the left of point B for energies lower than this energy, there can be no equilibrium. No, not at all. So this is called the Anton of Instability. Also, at this point beta, there's such an instability in the sense that what is in the spiral here, whatever equilibrium is here, is an unstable equilibrium. So you have instability in a twofold way: no equilibrium for low energies, and the equilibria that are inside the spiral are all unstable. Now, there is also another instability at point A. This instability means that if you go at temperatures lower than A, so if you increase beta, above this value of A, you will not be able to find any equilibrium state. There is this curve here, AB, this part of the spiral, AB, which is crazy enough, a branch of equilibria which are stable in the case that the energy of the system is constant. So statistically speaking, in the language of statistical mechanics, you have a microcanonical ensemble. And it is unstable if you consider temperature to be constant. This means a canonical ensemble. We'll have a case in the self-gravitating gas. It was the first system where it was identifying the fact that you can have an inequivalence of statistical ensembles. So the ensemble equivalence of ordinary gases breaks down in the case of gravity because the two ensembles have different stability properties. So the stability for a self-gravitating gas depends on the boundary conditions, actually. So if you have a gas that is whose energy is constant, does not interact with the environment, you can have equilibria at this branch AB, which, by the way, if you are careful enough, you will see that it is a negative specific heat region. And actually, in gravity, typically systems lie exactly, precisely in this region, AB, with a negative specific heat. These equilibria, again, are stable if you consider the, for systems that preserve the energy. You understand that in the canonical ensemble, you have interaction with the environment, you have a heat path. So what is constant is temperature, not the total energy. So anyway, this is very well-known stuff, or less well-known, but in any case, these facts that I present you here were for the first time, mentioned in 1968 in a paper by Wood and Lyndon Bell, or Lyndon Bell and Wood, to be more precise. So this is really old stuff, although the fact that you have inequivalence of ensembles was not really understood until very recently. I mean that there was a debate about what it means. Now, actually, these instabilities, the instability point A is called an isothermal collapse, and the instability point B is called a gravothermal catastrophe. The isothermal collapse, actually, it is a manifestation of Jeans instability. This can be proven analytically. I have done this. The case of gravothermal, so this applies actually to the universe. You're thinking that the gas is expanding. It is a part of the gas can be assumed to be in a canonical ensemble in the sense that it interacts with the rest of the environment. And as it cools down, you have an instability for certain values of temperature and for certain perturbations that are related to the size R here. So anyway, the gravothermal catastrophe, on the other hand, is relevant to stellar clusters and also to compact stars, but not exactly this gravothermal catastrophe. So anyway, I will explain what I mean. The thing is that I was working on this system during my PhD, and I asked the question, what happens to this direction of the spiral? So this spiral was well known, as I was saying to you. It is in the limit of in the Whitfield limit, so in Newtonian gravity. But I asked the question, what happens to this direction of the spiral for high energies? Now I found out that this was not answered, and I decided to answer it. So first of all, we have to understand what is the question. So how does a system of an ideal gas that is whose constituents are mutually interacting, all of them, with gravity, so a self-gravitating ideal gas, how does it behave at high energy? So at high energy, you have instabilities like Oppenheimer-Volkoff instability, and there is a confusion. I realize there is a confusion in the literature. So what is the relation to this type of instabilities, gravothermal catastrophe, Jeans, instability, isothermal collapse, and so on, with the relativistic ones? Are they related? Now, the answer, I will go to the answer of the question, is that you get another spiral. So on the left panel here, you can see the previous spiral, but you can also see how is the spiral transformed when you consider a rest mass compactness. So this is this psi here, 2g times m rest over rc squared. So this is the rest mass. As you increase this compactness, the rest mass compactness, or just think about the rest mass in a constant radius. So if you put in more mass, the spiral, the upper spiral, let's call it upper spiral, it's get distorted this way, you see? But there is also another thing going on. There is another spiral in the bottom for high energies. This is a different instability. This is a relativistic gravothermal instability. And why do I call it gravothermal? It's for a different reason for why people call the point B instability gravothermal catastrophe. Slightly different reason. First of all, you have only gravity and thermal energy. So this is one reason to call it gravothermal. But especially this instability that I had identified back in 2015 is that, and this was the basic question that I had. So first of all, you understand this, this is actually a thought experiment, okay? So you have only motion and gravity. But
sorry, this sign is units of mass, right?
no, it's dimensionless. It's dimensionless. It's a type of compactness, of rest mass compactness, that is a dimensionless number. Now, okay, thank you for asking me this. So let me say this, that I also identified that as psi increases, the two spirals approach each other and they merge for psi equals 0.35, where they become a point. Above the psi, there is no equilibrium, not at all. So I was saying that considering this a theoretical question, I will tell you about it. It has also some applications, or it could have. But what drove my interest from the start was actually this thought experiment, this simple question. You have motion, you have kinetic energy, thermal energy, but every type of energy has gravity. Okay, so thermal energy gravitates. Tolman said this. Einstein first told this, but afterwards, Tolman was the one that explicitly talked about thermal energy. Tolman in 1936. Now, the thing is that, okay, so you have two opposite effects coming from the same type of energy, thermal energy. Thermal energy, on the same time, generates a pressure pointing upwards, but on the same time generates gravity, which points inwards. So the question is, can you indefinitely heat a gas without generating a black hole or not? So this is the question. You have a standard, a self-gravitating ideal gas inside the sphere with standard with fixed radius, and you heat it up. Can you heat it up indefinitely? No. The answer is no. This is what I found. You cannot heat indefinitely. At some point, the gravitation of thermal energy takes over its gravitating effect. And the system becomes unstable. Now, for a different psi, you can, it's easily to depict, not that easily, but I could depict the double spiral in a single plot like here. So you can see the upper spiral is a reminisced, it is what is left from the Anton of Instability after you turn on relativity. So it is the transformation of Anton of Instability under relativity. But the lower spiral here is another type of instability. That is the relativistic gravithermal instability that is also the one generated exactly because thermal energy gravitates, and not only this. As I have shown in another series of papers, the reason is that the thermal energy, the thermal mass, the thermal energy here increases proportional to T, but the gravitational part of the thermal energy increases proportional to T squared. At some point, the gravity takes over. It cannot be otherwise. Now, as I was implying previously, there is also a possibility to have an actual application of this thought experiment and of this theoretical instability that applies to self-gravitating ideal gas. What I found is that if you substitute as the mass of the constituents of the gas, the mass of the up quark or the mass of the strange quark, you get the threshold temperature at about 10 to 100 MeV. Now, what this means is that above this temperature, your system collapses to a black hole. Now, this is precisely, not precisely, but this is approximately the range of temperature where it is found that proto-neutron stars that are the remnants of supernova that are really hot can get stabilized. So 10 MeV, from 10 to 100 MeV, again, is the temperature where it is believed that is the maximum temperature of a proto-neutron star. Above this temperature, you get a black hole. So what this means is that possibly this opens up the possibility that matter at these densities and temperatures behaves like a quark ideal gas. So it is like, it is not that crazy to think of this, that at high temperatures your gas becomes ideal, in the sense that what matters is motion much more than the mutual interactions. As you increase the temperature, you expect your gas to be close to ideal. So it's not that crazy that you find such good values. You also find very good values corresponding to the mass. So in another work, I have shown that the Oppenheimer-Volkoff limit, the original calculation that was performed in 1939, and gives a value for the critical mass of 0.7. If you increase the temperature, you get this curve here. And at temperatures that are related to this value, that are close to 10 or 100 MeV, you get about 2-point-something solar masses. Okay, you're very close to the maximum mass of a neutron star, and by a very simple system. Anyway, just to clarify here that this Oppenheimer-Volkoff limit, for those who do not know, corresponds to ideal neutron cores that are at 0 temperature. So this contribution refers to predicting or calculating how this limit of the ideal neutron cores depends on temperature. So this is a calculation. Now, if you consider at 0 temperature, like Oppenheimer-Volkoff here, but if you consider, in addition, nuclear forces, this limit may rise up to 2 or 2.2, 2.4, some people believe, solar masses. So this is why neutron stars are found in masses between 1.4, that's Chandrasekhar's limit, and 2-point-something. Just to clarify this. Now, there is also another part of my work that is very closely related to all the stuff that I talked to you, that I have talked to you about until now. That is the relation between dynamics and thermodynamics in relativity, and gravity in general, Newtonian, but also in relativity, especially in relativity. So you think about Einstein's equations. So you have in one part, you may think of geometry, and the other part you have matter. So matter, what matter does is dictated by entropy, you see. So I'm I'm investigating to what extent is thermodynamics implicitly included in GR, in general relativity. I will not go very deep into this because now, and knowing that I talk mainly to astrophysicists, I would like to talk about more astrophysical stuff related to observations. So let me go to the second part of my talk that refers to astrophysical black holes. I suppose you know the categorization. You may find stellar black holes. You may think of another range of masses that is from 100 to 10 to 5, where these are classified as intermediate mass black holes. These are especially interesting because these are not actually observed. So there are some observations in the lower limit that's about 100 solar masses by LIGO. And there are some observations in the upper limit about 10.6 or I'm sorry, 10 to the 6th, 1 million solar masses, or some fraction of it. But there is no, up to now, not an observation deep inside this range, like let's say 1,000 solar masses or 10,000 solar masses. Now, there are also supermassive black holes. We know there has been a Nobel Prize for them. And there are some speculative types of black holes called primordial black holes that are assumed to have not not being the remnants of stellar evolution, but supposedly they were generating in the beginning, in the initial eras of the universe, directly from a primordial gas. I will not be worrying about primordial black holes here, although it is a very interesting subject. I'm interested in stellar black holes and LIGO observations in the followings. So, okay, this is a depiction of the black holes. Now, this is not that good. This is not updated with new LIGO observations that were released on November 2021. Will give you a distribution of black hole masses afterwards. But before, I would like to point very interesting mass range that is from 50 to 130 solar masses. Now, stellar evolution and supernova theory predicts that no remnant, black hole remnant, can be found within these solar masses, from 50 to 130. However, let me note here that the lower limit and the upper limit, but both limits, but I'm interested more in the lower one, is not identified with precision. So some people argue it is 60, some people argue it's 52, 55, 65. Anyway, there is big, people are not sure. I would say it's from 45 to 65. This is the lower limit of the gap. So I will not get into detail. Why is this gap? It's because of per-instability supernova. If we believe standard physics and our supernova theory, you cannot expect a merger, a remnant in these masses. There is also a lower mass gap that is from 2.5 or 2 solar masses and to 5 solar masses. And this refers a gap about compact objects in general. And both mass gaps that are theoretical mass gaps are very interesting because we now have observations from LIGO. And if we identify objects, compact objects within these mass gaps, it is a challenge for our theories. I will be interested in this presentation in the upper black hole mass gap. Now, the black hole mass function, that is the distribution of masses, black holes, predicted by stellar evolution theory, may be depicted by this blue curve here that I have drawn for you, assuming that the lower limit of the gap is 47.5, I think I have put here. Anyway, now the thing is that LIGO has a bias towards identifying, observing higher masses. If you consider LIGO's bias, you should expect a black hole mass function that's almost flat. That's almost flat. So this is the theory, but what is reality? The actual observations of LIGO, and I have updated my data with the latest announcement of November, look like this. Okay, so here are actually the black hole mass function generated by LIGO's data. You can see here that one cannot be quite sure if this is a flat distribution. It is increasing. People are debating. Probably or surely we need more signals to be sure. But we are sure, people are sure, that there are observations within the mass gap. Now, the uncertainties? Yeah, I have not depicted them here. I have not, so I do not know. So I have not depicted them here. Okay, I will not go deeply into this histogram, so don't worry about it. Of course, you may worry, but you may, look into the LIGOS data. For our needs here, we do not worry that much because I will not try to model this histogram. I just depicted for you to get a qualitative idea of how is theory compared with experiment, just qualitatively. What I want to emphasize is these signals here, which are definitely within the upper black hole mass cap. Now, one explanation is that of hierarchical mergers. This means that you have two black holes merging. So you have a second generation of black holes. That is the remnant. And then this second generation black hole merges with another one, with another black hole, either first generation or second generation. And you can see, for example, if you have two black holes of 30 solar masses and they merge, you have one at 60, and so on. So there is a lot of work performed by many people on hierarchical mergers, but there is a problem. The problem is that when two black holes merge and they emit gravitational waves, there is a kick. This kick is so strong that it can, and it seems that in most cases does, eject the black hole outside the cluster where it is placed. So in order to have hierarchical mergers, you have to have clusters. You see my point? So if the second generation black hole, the remnant, is ejected from the cluster, where can it find another black hole to form a binary? You see my point? So hierarchical mergers work inside stellar clusters. These should be dense stellar clusters, and two candidates are globular clusters and nuclear star clusters. Especially in globular clusters, it is very hard to retain a black hole remnant after a merger inside the cluster. Of course, this is probabilities. Okay, there are some that can be, but are probabilities good enough to explain our observations? People work on this very intensely. There is another problem, and the other problem is that of the hierarchical merger scenario, the other problem is that the black hole remnant has a certain spin after merger. So there is a spin signature in hierarchical mergers, and LIGO in some cases can detect spin. On the other hand, observations show that most black holes have close to zero spin. So anyway, this is challenging for hierarchical mergers scenario. However, there is another scenario that we have introduced, that we have proposed, and me and Demosthenis Kazanas from NASA Goddard Space Flight Center back in 2019. And this is what we call the rapid gas accretion mechanism. This is what I'm going to talk about. But before I explain what is our suggestion, let me note that until 2020 and until September 2020, there was no observation within the upper black hole mass cap. There was no observation. So there were a lot of observations. I don't remember how many, but none was inside the upper black hole's mass cap. So the first observation within the mass cap was a big deal back then in September 2020. And LIGO announced, as you can see here, we inferred that the primary black hole mass lies within the gap produced by Pacesina per instability supernova processes. So they announced what people was expecting or was not expecting, that there is an actual observation within the upper black hole mass cap And I mean, coming from the members, the binary members, okay? One black hole was 85, deep in the gap, and the other was 66, close to the lower limit. But one of them was deep. There is also another significant thing about this observation. It was the first that was a black hole that was observed that is 142, that is within the classification of intermediate mass black holes. However, I can tell you that this is in the lower part, so people tend to not think of it that being significant. But anyway, this is considered significant by many people. What is for sure, what attracted attention of the community was that these black holes were deep in the mass gap predicted by supernovae. Now, actually, me and Kazanas and Dimos, we have predicted this 1 year ago. So our paper was actually not after the observation trying to explain it, but it was a prediction. So it was in 2019 that we predict that binaries of black holes within the mass gap can be observed by LIGO. Why did we believe this? Now, the idea is the following. I will not go deep in the chronology of the universe, but I will remark this age, this era here. The star and galaxy formation starts at about 300 mega years after the Big Bang, where stellar protoclusters are assumed to be forming. Okay, and these are supposed to be the seeds from which galaxies form, but also the seeds of globular clusters. Now, at the time, what you have is a lot of gas. So primordial protoclusters are supposed to be collapsed gas clouds, where stars forms in the early universe. Globular clusters are supposed to have evolved from these primordial clusters. And also nuclear star clusters is not clear if they are a direct remnant of primordial protoclusters, or they may be mergers, or all of these possibilities together. The thing is that primordial protoclusters contain a lot of gas, and after following the first stellar formation event in the cluster, there is believed to remain between 30 and 70% of the initial gas inside the cluster. Now, it is believed that the gas gets depleted at some point, and the reason is that you observe nowadays globular clusters, and they are depleted from gas. The time scale at which this happens, this occurs, that is the depletion of gas, is not calculated with detail. So it's from 10 to 100 mega a year. This is under debate. People work on this. How is the gas depleted from the cluster? Okay, but in any case, for sure, you cannot have gas depletion less than within 10 mega years. There is also something else that globular clusters contain. It seems that they contain two types of population of stellar population. So there is evidence that the gas remains within the cluster for at least 50 mega years. In any case, the thing is that we were thinking about it, and we realized that there are all necessary ingredients there for black holes to grow via gas secretion inside these protoclusters. Why? A black hole population exists. It is calculated the typical protoglobular clusters form from 100 to 1,000 black holes within 3 mega years. The reason is that these black holes are formed from very massive stars that burn their fuel very quickly. You see, so black holes form very early in the cluster. Secondly, mass aggregation. Black holes accumulate in the core. The tendency to thermal equipartition. Now, I mean thermal equipartition in the sense that I was talking in the beginning. So, I mean, our self-gravitating gas now is a stellar cluster. Our gas molecules are now stars. So you have stars that interact only through gravity. So thermal equipartition dictates that more massive bodies have lower velocity dispersion. They tend to accumulate in the center. This is called mass segregation. So black holes are generated very early, very, very early. They also are found in the core because either the massive star or the black hole itself will have a tendency to go to the center because of mass segregation, being much more, both of them, and both the massive star and the black hole remnant are much heavier than the average solar object within a cluster. And third, there is sufficient time window regarding gas depletion. So the gas accelerates mass segregation. The presence of the gas accelerates this phenomenon of heavier bodies accumulating in the center. The time scale is about 1 megayear. This is very rapid. So gas depletion proceeds at a time scale from 10 to 100 megayear. There seems to be enough time, there is time window for black holes, for stellar black holes, to grow via gas accretion in this gaseous environment significantly. So how much significantly? This was our question. Can we populate the mass cap? Is there time for the black holes to populate, to accrete such amount of gas so as to populate the black hole mass cap? This was our question, and Dimos Kasanas also had the idea and proposed that in addition to this, you make it hardening. So hardening means that the black holes come close to each other. Okay, so the idea is that just because of accreting mass, okay, accreting gas, so growing in mass, you would expect for simple dynamical arguments that you get hardened. So we calculated this, and we found a paper of John Hadjidimitriou, a very old paper, that where he considered the opposite problem. So it is a two-body problem with a variable mass that John Hadjidimitriou considered, but with a mass that is decreasing. So he was thinking about stars that emit radiation, they lose mass, you see? So we just reverse the time and you have the opposite calculation of two-body problem where the two bodies accrete increasing mass. So accrete gas and increasing mass. So what you get is this dependence of the accretion of the hardening with respect to the masses of the binaries. Now, why is it important to have hard binaries? The thing is that, first of all, in order to have a like observation, you have to have the black hole, the binary black hole to merge. Now, this means that you have the binary to form. Okay, it's not trivial. Why should the binary black hole form? Now, the answer, one of the answers, and it is one of the mainstream channels for the signals, is that this occurs exactly in clusters, in stellar clusters, because they are dense. The probability to have an encounter between black holes and third objects, three-body encounters, is high. And for this reason, stellar clusters, ideal environments for black holes, binary black holes to form. The other thing is that they should be so close enough, so you should have such hardness that there is time to merge so that we can observe them today, so within a Hubble time. So if you are able to identify an environment where black holes, both binary black holes, both are created or generated, and they can get to a hardness value that is compatible with observing them today, you are close to the truth. This is what I suppose. So anyway, so we did some calculations. We have found these are very preliminary calculations. We are working on it right now for more advanced calculations, but our preliminary results included in this paper that was 1 year before the first observation, so that not only you can have a population of the black hole mass cap, but also that the black hole mass function for lower masses gets a little bit shifted to higher masses. So you have creating gas that leads to have more mass in the range 20 and 30 and 40 solar masses than if you did not have it. So this was our proposal, the rapid gas accretion mechanism. There is a lot of work to do on this. How does rapid gas accretion affect the merger rates? What is the dominant challenge for populating the mass gap? What if you consider both phenomena, gas accretion, hierarchical mergers, and so on? Now let me move on with another phenomenon that is called gravitational Brownian motion, and is related to stellar clusters and also to these calculations about black holes inside stellar clusters. So I told you before that black holes are heavier, much heavier than the average mass within a cluster. It's about 0.3 solar masses. Typical black hole is 10. And we have LIGO identifies black holes with 30, 40, and 60, and so on, solar mass. So what is the situation? I was thinking about it. So what you have is a few heavy bodies immersed in many much larger bodies. So this resembles Brownian motion. Okay, what is Brownian motion? You have a few heavy bodies thrown into water, for example. So you have very light molecules of water, and the random motion of water provide energy to your heavier bodies and makes them disperse. So I was thinking that, okay, this typical, this ordinary Brownian motion is based on electrodynamics. Okay, this is an effective electromagnetic interaction, effective electromagnetic interaction in water. What if I replace this interaction with gravity? Then what I will get is gravitational Brownian motion. Chandrasekhar had this idea first in 1943. However, he restricted himself in homogeneous configurations. So he did some calculations about Brownian motion, gravitational Brownian motion, but he considered only homogeneous configurations. What I did in 2021 is to generalize this for inhomogeneous configurations. So why did I do this? For obvious reasons that realistic astrophysical systems are not homogeneous in any way. So in homogeneous configurations, both in density and temperature. And what I mean by temperature is velocity dispersion. So in stellar clusters, you have a distribution of density and velocity dispersion with radius. This both change. So you have homogeneous configurations. So this is the calculation I did, and I proposed an equation that describes precisely gravitational Brownian motion as an inhomogeneous diffusion. And my application was black hole populations in globular clusters. So, yeah.
Can you have homogeneous cases, conditions?
Sorry?
Can you have homogeneous conditions if you consider stochastic motions?
If?
So Brownian motion means the particles, interact. So there's some friction, this interaction produces.
So you're saying that homogeneous systems are not realistic when you consider Brownian motion.
Yes.
Yeah. So there is an approximation that is an approximation of Chandrasekhar, and there are limitations of this approximation. So it may work under certain conditions and for certain parts of a system, but it may not work in general. So what I consider is not homogeneous, exactly inhomogeneous. So let me focus on this. And the idea is to describe precisely black hole populations in globular clusters. And my question is that, can this help black holes being retained inside the cluster. Now, the thing is that people for many years believed that globular clusters and dense stellar clusters do not contain, especially globular clusters, do not contain many black holes. The reason is that there is this instability, another instability called Spitzer instability. That's exactly precisely due to mass segregation that makes the black holes collapse because of them being more heavy than the rest of the stars. So make them collapse very, very violently. And eventually they get ejected out from the cluster. So if you can show that you can violate Spitzer instability, you can suggest that black hole subclusters may be retained inside the globular cluster. And this is what I believe is the case. And this is what I have shown here by considering gravitational Brownian motion as a homogeneous diffusion. And in this moment, let me explain how does gravitational, or not explain, but just to sketch how does gravitational Brownian motion emerge in such a cluster. It is because of the granularity of the system, actually. It's the granularity of the system that makes such the random fluctuations of the mean field that are generated exactly by close encounters. So it's the granularity of the system that creates this type of pressure. It's the Brownian, the homogeneous Brownian pressure. So there is a lot of math involved. I will not go deep into this. I propose a homogeneous Brownian equilibrium. This is not a Boltzmann equilibrium. You can see here you have a dependence of beta and r. You have here beta of r times phi prime, anyway. The theory seems to agree with some simulations that I performed. And most importantly, you violate the Spitzer threshold. So what I suggest is that in homogeneous Brownian motion, so this effect, the random fluctuations of the gravitational field generate a pressure in Brownian particles that for me are black holes that allows for a black hole subcluster to form, at least in certain values of our parameter space. So there should be some, if not many, I'm working on it, clusters that can preserve black hole subclusters inside them. So this is very important for merger rates of binary black hole mergers. You see? So if you have a black hole subcluster, this is a dense subcluster of black holes. You expect to have higher merger rates than if you assume that this black hole subcluster were dissolved in the first 100 mega years of the life of the cluster. It's a very different situation if the clusters of the subcluster can live for a longer time. Now, this idea applies also to dark matter, actually. And we have done some work with Amr Elzan and Joseph Silk on fuzzy dark matter and have shown that supermassive black holes will be ejected exactly because of Brownian motion generated by the fluctuations of the field. Put some limits. You may also explain some observations in dwarf galaxies. I will not get deep into this. I don't want to go into dark matter now, but there was another application. Now, what to go on from there? Okay, these are ideas I'm working on. Let me not get deep into this. I only wish to mention that, you know, that Einstein was the one who explained Brownian motion. And you know what he used? If you go through his paper, I do this, and go to the source and read these papers, and you will see that he uses the paradigm of osmosis. This is osmosis here. Huh? Anyway, so what I'm working now is this. I will not reveal more detail about it, but I just point this analogy. So let me close with another effect of or another application of statistical mechanics of gravitational systems. These are called, now this effect is called gravitational phase transitions. Let me very briefly introduce what is called resonant relaxation in stellar systems. This was an idea by Rauch and Scott Tremaine back in 1996. The idea is that, okay, let me just note here that the kinetic theory of gravity is a flourishing field. For decades, it was a dead field, but nowadays it's flourishing. At least for the last 10 years, there is a lot of work being done. Anyway, but let me describe briefly what is resonant relaxation, introduced firstly by Rauch and Tremaine. So the idea is that in certain stellar clusters, especially the ones that have a dominant central potential. So, for example, you have a nuclear star cluster which has a supermassive black hole in the center. Then, if you approach to a radius where you find mostly regular orbits, nearly Keplerian orbits, there is a possibility to have a timescale hierarchy of relaxation. So you have a different timescale for relaxation of the orientation of the orbits, of the orbital planes in space, and a different timescale for relaxation, for two-body relaxation, so the relaxation of the energy, and maybe a different timescale for the relaxation of eccentricity, so the precession. So I will focus on the reorientation of the orbits. This means that the magnitude of the angular momentum of the orbit relaxes independently in a different time scale than the rest of your degrees of freedom. So you have not the magnitude, the vector, sorry, the vector of in the reorientation, the direction of the vector of angular momentum relaxes in a different time scale than its magnitude, which is called the precession. This is called the scalar resonant relaxation. Reorientation of the orbits is called the vector resonant relaxation because it is the vector of angular momentum that relaxes, and the two-body relaxation is the energy. So, vector resonant relaxation is a case of internal thermal equilibrium. Another system that does this are nuclear spins. So, in a nuclear spin system, you have the nuclear spins that come to a thermal equilibrium independently from the motional degrees of freedom. See, this analogy is straightforward. In gravity, or in the case that you have regular orbits, nearly Keplerian orbits, not chaotic, not irregular, but regular, then you have not spin, but the direction of angular momenta relaxing independently in a time scale different than the other degrees of freedom. Anyway, so in 2017, with Cox and Tremaine, we worked on vector resonant relaxation, and we created a mean field theory of vector resonant relaxation. So we identified new types of phase transitions that are called gravitational phase transitions. So what we did is that we perceive the different states of a system's orientation of vectors of angular momenta as different phases of the system of matter. So geometry is correlated with thermodynamics. So what we found, I will not go into the theory, but I will show you these phases. We call them uniaxial, biaxial, and disordered phases. You see the uniaxial phase is actually a disk, and the disordered phase is actually a sphere. So you have a phase transition from a sphere to a disk. Anyway, there are observations that look a lot like our biaxial states here in the Milky Way, inside and close to the center. But what I would like to emphasize is that our theory with Cox and Tremaine had a limitation. That is, we did not consider back then the motional degrees of freedom of the orbital planes. So we do not consider the precession of the orbital planes. We assume that the energy was solely the gravitational energy. If you have a look at our Hamiltonian here, we have only potential energy. Now, this is good enough for in the case that you have a really supermassive body in the center, like a supermassive black hole. So, because the precession of the orbits is very, very, very small, but I was not absolutely satisfied and would like to prove, and to identify what are the limitations of our approximation. And recently, I calculated the precise mean field theory of resonant relaxation, including the kinetic energy terms. So what I did is that I considered also the kinetic degrees of freedom. So just don't throw away anything by hand, but just start from the new-body Hamiltonian and take an average over the precession time scale of the orbits. Assume that there are orbits, okay, this is an assumption from the beginning that you have irregular orbits, and take the mean at a certain time scale, the mean about the orbit certain scale. Do a lot of math, and you will find out this Hamiltonian, you will come up with this Hamiltonian that is the general Hamiltonian of vector resonant relaxation that includes two terms that are kinetic and depend on the moments of inertia of the disk. So the difference with our previous theory is that now we have included the possibility for the disk to have inertia, okay? So they can vibrate. And also I have shown, okay, this is an example of how an orbit, when it is calculated, a precession orbit, okay? When it is calculated in many precession periods, looks a lot like an annular disk, okay? So the effective system described by this Hamiltonian is a set of disks that look like this and interact mutually with gravity. This is what is described by this Hamiltonian. Anyway, this is the math. You can find details. The thing is that I was able to show how you can have, in which cases you can neglect actually these perturbations of the orbits, and also expand our theory of gravitational phase transitions to the case where you do not have a supermassive object in the center. So I saw that you may have vector resonant relaxation also in globular clusters if they, for sure, if they have an intermediate mass black hole in the center, it may be even in the case, even in the absence of a central massive object, at least certain radii. Anyway, close with this. So I would like to emphasize the future research prospects, especially related to LIGO. Okay, I believe this is one of the most interesting directions to go on, and consider the rapid cluster creation in protoclusters in correspondence with the hierarchical mergers. Okay, and find out if the LIGO observations can be explained by both these effects, or if there is something else going on with the black hole mass cap and our theory of supernova. Okay, I close with this. I do not wish to occupy more time, and thank you very much. Sorry?
There are questions online.
Yes, okay. I understand your question. I have run my own simulations. I can show you, and I have shown before one right here. However, I should note, okay, here is the result of my simulations and the theory on top of it. However, I must emphasize that you have to account for the time scales involved. For how long can this subcluster live, actually? What are your initial conditions? So you cannot compare simulations generated for other purposes. I mean, that you have to run your own. Hopefully, I will do more detailed work in the future. This is what I can tell now. Yes?
So in the very beginning, when you were discussing about this instability, you mentioned that gravitational waves can produce something in the computer. That gravitational energy can produce thermal energy. Yes. So I didn't understand this.
Okay, so I think it was 1938 or something like this, that Tolman and I think independently, Ehrenfest. In fact, they have a paper that they're both the authors. So nowadays this is called Tolman-Ehrenfest effect. So they found out that at equilibrium, at thermal equilibrium, you do not have a homogeneous flat distribution of temperature in relativity. So, first of all, in gravity, if you think about it, your thermal equilibrium states, and thermal in the sense you understand now what I mean thermal, are not homogeneous. So in an ordinary thermodynamics, your equilibrium states, this is the definition of equilibrium, are homogeneous. Okay, so you take a gas and put it in a corner, leave it, and homogeneously distributes in the room. In gravity, if you take a gas and leave it alone, it will not relax in homogeneous state. Regarding density, you will have a distribution of density. But also, if you account for relativity, not in Newtonian, in relativity, there is a distribution of temperatures. And this is called Tolman-Ehrenfest effect. This is dictated by maximum entropy. When you take into account the entropy of gravity in your calculations. So temperature, thermal energy, or the temperature density is an artifact, is not an artifact, is an outcome, a result of the fact that thermal energy gravitates. So it's a lot like density. So density is inhomogeneous, but since thermal energy gravitates, it's also inhomogeneous in an equilibrium. So it has to support itself against its own gravity. Now, I suggest you could read some of this if you're interested. But this is what I can tell now. Yes?
So we discussed how the thermal instability can be applicable to neutron stars when they are very hot, very young, and so forth. What happens in the early universe where everything is very hot at some point? Would that have some applicability?
Yes, thank you. Did you want to say something? I interrupted. So what I believe and what I understand, although I'm not that much of an expert regarding the early universe cosmology, but I understand that the radiation era is pretty much includes this instability. I mean that at very high temperatures, high energies, the equation of state of an ideal gas is equivalent to radiation equation of state. You see? So in order to find some effect in the early universe, you have to identify some era in between the matter domination era, that is the Newtonian quick field limit actually, with respect to the equation of state, and the radiation era. So if you find a way to go in a continuous way from the radiation equation of state to the matter domination era, you see my point? Huh? So then you may be able to identify some effect, you see. But I understand that in standard cosmology, you assume that, you know, this is, I don't know, this is a jump from radiation to matter. But if you manage to account for the equation of state that changes with temperature, you may be able to identify some effect. But I don't know if this is useful. I would be very much interested in working on it. If someone is an expert in early universe cosmology, I do not know. I do not know if there is some effect. Maybe not.
Are the conditions in the matter dominated era early still relevant to your? I mean, are the compactness, is this compactness criteria relevant for this?
No, it's just Jeans instability.
No,
So Jeans instability is this point here. Sorry, yes?
Yeah, go back to the.
Yes?
No, the plot.
I'm sorry.
There. So this high energy spiral, right? And your compactness criterion for stability. Would it apply? Is it relevant for the early universe? Could it lead to the creation of
This is what I told before. That I don't know actually, but it could. But you have to try out into total calculation. So you have to consider the equation of state.
No, even in forget about the radiation, right? Even in the matter domination.
I answered this. No, in the matter domination era is just Jeans instability. So what is relevant is only this point here. Hey, this is what I believe. I mean, maybe it's something to discuss. This is what I understand right now.
Just a question about the globular clusters, right? So one of the arguments is that you said that at the center of the globular cluster, you can actually cover multiple binary massive black holes, right? But I was wondering, you may have done the calculations, and sort of like the age of the globular clusters in our galaxy ranges from 3.5 billion years to 10 billion. And I presume you argue that light will detect gravitational waves which come from proto-globular clusters in distant galaxies, right?
No, not necessarily. So the thing is that, not necessarily. The thing is that the time of the merger is different than the time of the generation of the binary. So you may have a binary that is formed in the proto-cluster, but this may emerge in 10 gigayears from the time, you see. The thing is that what is actually very occupying our minds with Demos Kazanas is that you should have some X-ray signals actually from these proto-clusters, you see. So if you have actually a gas separation mechanism at the time, you may detect it through X-rays, but you expect this to be a very high redshift. And now there is no operating system that can detect this, but there is links that will start operating.
You will detect X-rays from the binary black holes?
No, not necessarily binary, but just a single one at high redshift. The thing is that links can go very deep and have very high redshift.
I understand, right? But I
Yeah.
think, I mean, Andreas is not here. Some of us students know that I think it's very difficult. I mean, I don't know whether you could see how you could distinguish that from X-ray binaries that you see. And
I really don't know.
Yeah.
Yeah, I
And
really don't
also,
know.
one of the things that puzzles me is that, you know, globular clusters are sort of like they have no angular momentum signature, and so how you will actually accrete gas to form supermassive black holes and solve the angular momentum dissipation problem, right, in these systems. That's
Now,
because this is mostly bond-like collapse, right? What these are for. So
this is not relevant to our suggestion because we do not consider our results does not show the formation of supermassive black hole, not even massive black hole in the sense that you are 1,000 solar mass and so on, but a very small increase of mass. So you go from 30 to 40, or from 40 to 80. You see, so it's not.
Have them there.
Yes. So the black holes are already there. They are generated from massive stars. They are supposed in a typical cluster to be about 500 of them, and their masses range from 5 to 50, let's say, and they are inside gas. So our calculations show that they grow by a few solar masses, some of them, and the ones that can be close to the center. So there's no problem with what you are thinking about. It's not that much of a different situation.
In the same bit of discussion here about the what does the calculations do variation, for example, of the function of the stars, and how this would affect the calculation of the emission black holes, and then the results with respect to the mergers, etc.
Now, we have not performed these calculations. This is under development to estimate merger rates and for different mass functions. So interesting. Up to now, what we have only shown is that the time window is sufficient for a few of black holes, for at least some of them, to increase in mass inside the mass gap. But the quantity and the dependence of, the black hole mass function, the final black hole mass function, on the initial ones, on the initial one, on the, the gas proportion, on the type of accretion. We have considered isotropic accretion and Eddington accretion. Okay, so there are a lot of parameters. It's a big parameter space that it requires a lot of work. So unfortunately, we have not done this. We're working on it. How with the more massive primordial black holes? Okay. Okay, this is very interesting. I've told you in the beginning that I will not consider primordial black holes, but this is very interesting, guys. So there is a lot of work to be done. Yes, this is very interesting. So you may consider an addition to the population of black holes, the stellar black holes that are generated by stellar evolution, normal stellar evolution. You may assume that there are also primordial black holes, you see. And of course, you should expect some differences. I can see the point here that maybe if you have primordial black holes from the start, you are led to the formation of intermediate black hole. Actually, yes, and through both gas accretion and hierarchical mergers. This is very interesting. I mean, a lot of work is already being performed in this area. There are no definite conclusions that I know of. I mean, these are very open subjects. First of all, people do not know, are not sure about. I mean, there are many possible origins of primordial black holes. There is uncertainty in what is the black hole mass function for stellar black holes, needless to say for primordial that are so speculative. So this is very interesting, but people work with it.
Okay, let's thank Zaharias again. And we'll be around for the next few months for sure. So I guess there are people who are working on this aspect, but at least from the point of view of the observations that interesting discussion. Okay.
Thank you very much.